Hi friends, we are going to learn today divide and conquer technique. Inside we are going to discuss binary search. As in previous class we have discussed what is the divide and conquer technique, general plan, master theorem, right? Now in this we are going to discuss very important algorithm, binary search. Now what is binary search? Binary search is technique or algorithms to find a proper key element into the given list of elements. Say we have 100 elements, out of that we need to find some particular key elements, right? So we are going to apply binary search to find those key elements in lesser amount of time. Let us see that in previous topic we have discussed even sequential search, okay, that is called linear search, right? And in a linear search what happened, we have done the searching of an element from the left element to last element, depends on the problem scenarios, and we accordingly perform the task. While in binary search we are going to perform the task based on middle element. Now how to find out the middle element? We are going to find out the middle element based on index. So array will have their index, each and every value will have their own index. So that index we are going to add and divide by 2. We will get the mid positions, mid elements, and that we are going to compare and find key elements in given list of elements. Here is binary search. So let us see that how exactly it is. First, what are the condition is for binary search is all the elements in the list must be in sorting. All the elements in the list must be in sorting order or sorted order. Now, what is that? It can be in increasing order or decreasing order, but must be in sorted order. Then only we are going to apply binary search. Let us see that some input, that element is not in sorted order. Then this is our duty. Before applying binary search, we are going to sort the elements in ascending order, then apply for binary search algorithm. Then only it will work. Otherwise, it will not work. Okay. And key element to be searched based on middle element index. Key element to be searched based on middle element index. We are going to find out the mid elements and then we are going to compare with the key elements. If it is same, okay, that particular element is found. Otherwise, element will be there in the left side of the arrays or right side of the array. Let us see that what I am trying to tell you. Say here we have elements called 5, 10, 15, 20, 25, 30. Alright. How many number of elements we have? Here we have 6 elements. So we are going to write the index 0, 1, 2, 3, 4, 5. Right. So first time when you are going to find out the mid element will be searched based on index, low index plus high index divided by 2. So here what is low, friend? Low is 0 and high is 5. So it is 0 plus 5 divided by 2 is 5 divided by 2. Remember that we are dealing with index, and index never be the fraction. It will be always positive integer, or we can say non-negative integer including 0. So 5 divided by 2 we are going to write it as a 2 as a mid element. So now we got the mid element as a 2, right? Here is based on this we are going to search key element. Key element is say as for example 15. Key element is 15. In that case, what will happen? We are going to check whether 15 is present in the given list of element or not. How are we going to check it? We are going to check based on if key is equal to A of mid. Look, key is 15 is equal to A of mid. A is name of the arrays. Mid index is 2. So we are talking about A of 2. A of 2. What is the value? 15. So 15 and 15 both are equal. It is condition is true. If condition is true, we can say that element is found. Or you can say that key element is found. Where it is found? Found at index 2, but it is position 3. 1, 2, 3. Position is 3, but index is 2. So key element is found. So for that, even in previous class I said you, real life position, natural number positions, we are going to write I plus 1, index plus 1. So 2 plus 1 is 3. Say in the same scenarios, for the same given problem, say key element is 5. Key element is 5. What will happen? We are going to perform the task. If key element is 5, again you are going to perform, just ignore that part. Key element is 5. We are going to find out the mid element. Mid is equal to low plus high divided by 2. So it will be low plus high divided by 2. So 0 plus 5 divided by 2. We got 2. Now we are going to compare. Is key element is 5 is equal to A of 2 is 15. Is 5 is equal to 15? No. False. If it is false, it means that either key element is lesser than A of mid, key element is lesser than A of mid, or key element is greater than A of mid. So remember that. If it is not equal, then there is two scenarios. Maybe key is lesser than A of mid. If key is lesser than A of mid, it means we have to go and search in left side of the mid element. Means we are going to search in this part, right? If key is greater than A of mid, if it is not equal, if both are not equal, there are two different cases. Either key will be lesser than A of mid or key will be greater than A of mid. Okay. If key is lesser than A of mid, problem is going to be, or key element is going to be in this part, right? If key is greater than A of mid, then problem is not here. Problem is going to be in this part. So either you are going to search in the left array or you are going to search in the right array. So at one time we are going to perform the task one of the half of the arrays, not complete arrays as we are doing in other problems. Okay. If k is lesser than A of mid, now what will be the problem, friend? Key is present in this part, so low will be remain low, and what will be high? High is mid minus 1. So in this case, high is mid minus 1. So that we are going to find out the new high values. Earlier high index was 5. Now high index is mid minus 1. 2 minus 1 is 1. Remember that if key is greater than A of mid, second part, high is remain high, but low part in this array, low part is changing. What will be the low? Low we are going to write it mid plus 1. So this is very, very important in a case of binary search to find the proper index. In the case of key is greater than A of mid, find low index. Key is lesser than A of mid, find high index. So high will be mid minus 1, low is mid plus 1. If you are doing so, we are able to perform the task properly. So say, as for example, here 5 and 15 is not equal. It means it is going to be one of the case. Either key is lesser than A of mid or key is greater than A of mid. So key is 5, A of mid is 15. So 5 is lesser than 15. So we can say that 5 is lesser than 15. If 5 is lesser than 15, we need to compute new high values. So high is mid minus 1, 2 minus 1 is 1. In these problem scenarios, low is remain low, low is 0 only, low is 0 only. And now we are going to recompute this mid position. What is mid positions? Mid is equal to low plus high divided by 2, 0 plus 1 divided by 2. So it is 1 by 2. What I said you friend, we are not looking for the fractional values. So 0.5 is remain 0. Now we got mid is 0. Now again you are going to compare, where key that 5 is equal to a of mid. Now new mid you got 0, a of 0 is 5. So is 5 is equal to 5? Yes, condition is true and element is found, right? Similarly, say here we have a problem scenarios. All of you please concentrate. 0, 1, 2, 3, 4, 5. Now in this case, say we have a key as 25. Key is 25. We are not going to compare these all elements, just we are finding first mid element. Mid is low plus high divided by 2, 0 plus 5 divided by 2 is 2. Then you are going to compare, is 25 is equal to is key is equal to a of mid. So is 25 is equal to a of mid, a of 2 is 15. No, false. It is not equal. It is not equal. False. If it is false, then there is a case key element is greater than a of mid or key element is lesser than a of mid. So let us see that key element is 25. So it will go in case key is greater than a of mid. Key is greater than a of mid. In this case, what will happen? What I said you friend? If key is greater than a of mid, we are going to compute low index. High will be remain high. We are going to compute low index. So low is equal to mid plus 1. Mid index is 2 plus 1 is 3. Low is 3 and high is remain high. So high is remain high means what? High is 5. Now you are going to find out the new mid positions. Mid is equal to low plus high divided by 2. 3 plus 5 divided by 2 is 4. Now let us see again. We are going to compare key element. Okay. If key element is whether equal to a of mid or not. So key is 25 is equal to a of mid, a of 4. A of 4 is 25. Both are equal. Hence 25 is present in the given list. What I am trying to say you, when you are searching 25 position is what? 1, 2, 3, 4, 5. If it is linear search, we required 5 comparisons. But here we did 1 comparison here, 1 comparison here. How many comparisons is required? Only 2 comparisons to find 25 in the given list. Okay. Similarly, when we have discussed with key element 5, key element is present at the first positions, right? And here still it's required 2 comparisons. Look, for key element 15, key element is 15 present in the third positions, but it's required only 1 comparisons to find out, even though it is in third positions. So likewise, we are going to perform the task and we are going to write the algorithms, okay, for binary search, and we are going to discuss, right, a time complexity of binary search as well. Algorithm for binary search. Let us see that. Binary search. There are 2 algorithms for binary search. Either you can write recursive algorithms or non-recursive algorithms. Recursive and non-recursive. So say we are going to write binary search recursive algorithm, right? Binary search recursive algorithms, and we are going to discuss binary search non-recursive as well. So here we'll have array int a, right? We'll be having int low index, int high index, and int key element to be search. Look, if low index is greater than high index, then we are not going to perform the task. Okay, it will simply terminate. So say if I'm going to write int mid, if low is greater than, right, high, then return -1. Why it is? If low index is greater than high index, we are not going to perform the task. Function will terminate from there only. Else we have discussed 3 cases. What are the cases? First, we are going and finding mid is equal to low plus high divided by 2. Once it is done, mid element, then what we did, friend? 3 comparisons we have done. So let us write all the comparisons. What is first comparison is, if key is equal to a of mid, if this is the case, then return mid plus 1. Why return mid plus 1, friend? Because mid is a index, start from 0, real life position is index plus 1. Or even you can write return mid, but keep it in your mind that index start from 0, hence it is, array index is lesser than the real life positions. Sometimes in the books you can find out it is written mid, okay, that is represent for index. Else if key is not equal to a of mid, then what could be? It can be key is lesser than a of mid. If key is lesser than a of mid, it means what? We are going and searching in left side of the arrays. In that case, function calling itself is called recursive function. So we are writing return. What is the name of functions, friend? Binary search recursive. And what are the parameters we have? A is array, low index. Key is lesser than a of mid. What I said? Low will be remain low. So it is a low only. And I said you high will change. High will be mid minus 1. Mid minus 1. And key element to be searched is remain same. So this is a function calling itself. It will go and perform the task again and again. Else if key is equal to mid, if not, key is lesser than a of mid, if not, then there is a third case, key is greater than a of mid. In that case, what you are going to write, friend? Return binary search recursive. A is name of the array. Key is greater than a of mid. It means what? Low index will change. Low will be mid plus 1. So low is mid plus 1. And what is high index? High will remain high. So high is remain high and key element is as it is. So this is binary search recursive algorithms. We have not done anything. So whatever the things we have discussed in example, same things we have written here, rewrite here. Key, case equal case, key is lesser than a of mid and key is greater than a of mid. See, by default this case is entering into key is greater than a of mid. It is understood that key is greater than a of mid for the third case. Look, have we used here any for loop, while loop, do while loop? No. Hence it is recursive. No. Same kind of concepts for binary search we are going to apply while you are writing non-recursive algorithm using loop concept. So let us see that. Binary search iterative algorithms. Here we have a right? That is what it is, arrays, or even you can write it number of elements we have and key elements. Look what will happen here. In this particular case, since you are going to use the loop, right? So we are going to write the conditions like if. First of all, what we are going to find out? We are going to find out mid positions, right? Mid positions of the elements. Once you find the mid positions of the elements, then you are going to compare it whether it is equal or not equal. Otherwise, we are going to, find the low index and high index. So let us see that. While low is less than equal to high. While is loop, low is less than equal to high. This is the case. Then first we are going to find out mid positions. So let us see that we are going to find out mid is equal to low plus high divided by 2. Low plus high divided by 2. Mid position is ready now. What is the case? When low index is lesser than high index, right? Now we are going to check the condition. What is that? If key is equal to A of mid, then if key is equal to A of mid, what are we going to do it? We are going to return mid plus 1, or you can print it here, printf element is found at so and so positions. You can write it here, printf key element found at %d positions. And what is percentage d? Percentage d is mid plus 1. So like this also you can write it. Key element is found at percentage d, that is what position is mid plus 1. If key is equal to A of mid, we have written that, else there is a case, else if key is lesser than A of mid. If key is lesser than A of mid, it means what? You are going searching in the left arrays. If you are searching in the left arrays, then you are going to write high is equal to mid minus 1. High is equal to mid minus 1. Else low is equal to mid plus 1. So there are three cases. Either going to say that it is equal, or key is lesser than A of mid, high is equal to mid minus 1, or key is greater than A of mid, low is equal to mid plus 1. So that we are going to write it again and again. Thereafter what will happen? There is a case while is not true. Not true means what? While a situation where low index is greater than high index, in that case we can say that otherwise we are talking about return minus 1. Okay, what is the condition? This is when if low is greater than high index, then it will return minus 1. So this is the algorithms for the binary search, iterative functions and recursive functions. What we are trying to discuss here is at any moment of time we are going to search either in left side of the arrays or right side of the arrays, right? And keep on you are going to compare with mid positions of the elements. So let us see that. If you are searching any of one half of the arrays, can we say like that T of n by 2? Reason is problem size is divided into two parts, either left side of the arrays or right side of the arrays. Hence problem size will be n by 2. Problem size is n by 2 plus what we are doing after finding the mid positions, we are comparing mid positions with the key element whether it is equal or not equal. So if it is equal, we are going to perform the task, right? So one comparison is done. So each and every when you are finding the mid positions of the elements, we are going to perform the comparisons. So basically T of n by 2 is what? Time taken to perform any one side of the array, any one side of list. What is that? Half list. Okay. Time taken to perform any one side of a list. And what is 1? 1 is time taken to compare with mid element. Time taken to compare mid element. In that case, can we find out the time complexity? Yes. T of n is equal to T of n by 2 plus 1. What is A? A is 1. What is B? B is 2. And what is D? 1 can be written as a n to the power D. So D is 0. Right? So hence n to the power 0 is 1. So in that case, B power D, B power 0 is 1. So 1 and 1 both are equal, right? So we can say that this is the case of A is equal to B power D case. In that case, we are, as per the master theorem, we are going to apply second concept, theta of n to the power D log n base 2. Hence, theta of n to the power 0 log n base 2. Hence, it is theta of log n base 2. So, time complexity of bandit search is theta of log n base 2. Theta of log n base 2. So, remember that when we are talking about best case time complexity of binary search is omega of 1 when key found at mid position. When key found at mid position, that is time complexity will be T of n will be omega of 1. Only one comparison is required. Otherwise T of n is equal to theta of log n base 2. In worst case, time complexity will be theta of log n base 2. So let us see that. Time complexity using backward substitutions method, right? What is that? We are first we need to write the recurrence relations, and recurrence relations we have written what? T of n is equal to T of n by 2 plus 1 if n is greater than 1, right? And if n is equal to 1, what will be the time complexity? It is 0, because if it is only one element, are you going to divide the array into two parts? No. So, are you going to use the recurrence relations, recursive functions? No. If you are not going to use the recursive functions, hence time complexity is 0. So, this we are going to use T of n is equal to T of n by 2 plus 1 as a recurrence. Then look, T of n becomes Tt n by 2 plus 1. So what will be T of n by 2? So just n by 2 you replace by n by 2. What will happen? T of n by 4 plus 1 plus 1. Look, T of n by 2, if you write in this format, T of n by 2 is equal to T of n by 4. N by 2 divided by 2, n by 4 plus 1. So at the place of T of n by 2, we are going to write it T of n by 4 plus 1, and this one is original. Look, n by 4 can be written as a T of n divided by 2 square plus 1 plus 1. Look friend, we are writing n divided by 2 square, but after dividing again and again, it has to stop somewhere else, right? And we'll see that recurrence relation is n is equal to 1. When we'll get 1 here? When we'll get 1 here? When it is n divided by n. We'll be getting here 1. Once we're getting 1, then this recurrence relations will be terminated. So, we are going to consider, okay, consider n is equal to 2 power I. N is equal to 2 power I. It means after ith iterations, we'll be getting 2 power I. Right? So, in that case, what will happen? These are first iterations, second iterations. After ith iterations, what will happen here? 2 power 2 times 1s. Hence, we can get it T of n divided by 2 power I plus 1 plus 1 plus 1 plus 1. How many times? I times. Done? N divided by 2 power I. Both are equal. Hence, this value is T of 1 plus 1 plus 1 plus 1. If 1 plus 1 plus 1 5 times you are going to add, it is 5. So, 1 plus 1 plus 1 I times you are going to add, it is I. Right? And T of 1, if n is 1, time complexity is 0. So, this is 0 plus I is equal to I. Right? So, you got I, friend. Now, do you have I in this term? We don't have I here. So, what will happen basically? We are going to find I, because I is not the part of the problem. So, if we will take log both sides, take log both sides. What will happen here? Log n base 2, right? And here we have log 2 power I base 2. We have taken base 2 because we need to take this I outside, right? So, this is basically I log 2 base 2. Log 2 base 2 is 1. So, hence we are getting I. So, what is the value of I? Value of I is going to be log n base 2. Hence, time complexity of this problem is T of n is equal to I. Hence, we can say that T of n is equal to theta of, what is I value? Log n base 2. Log n base 2. So, this is the time complexity while you are applying backward substitution rule, and we have done with time complexity using master theorem as well. Master theorem as well, we are getting log n base 2. Now, when you are dealing with the linear search, right? This is also searching technique, time complexity to find the key element is present in the given list of element. Here we had case, right? In worst case, it was theta of n. right? Best case time complexity was omega of 1 when element found at first positions, right? Similarly, when you are talking about binary search, worst case is theta of log n base 2 and best case is omega of 1 when we found with mid positions element, key present at mid positions, right? Then it's called best case. So compare here T of n log n base 2 as per our order of growth, right? Concepts, log n base 2 has lesser values compared to theta of n. Hence, binary search is more efficient, more effective compared to linear search, right? So this is what conclusion out of this searching technique. Since we have learned both the searching technique, we compare it and we found that log n base 2 is having higher efficiency, or it is more effective, or it will take lesser amount of time to perform the task compared to linear search. So we will stop the class here. Thank you very much for this.